So it should be somewhat natural to think there is symmetry we can exploit for circular patterns. And there are three forms in particular that we're going to look at here. We have symmetry with the polar axis, symmetry with the angle pi over 2, and symmetry with the pole. Where symmetry with the polar axis can be thought of as something like horizontal symmetry over that axis there. And we notice that by being able to exchange theta with negative theta and not have it affect the results. In our second case, if we're looking at symmetry with the angle pi over 2, that is, we're looking at symmetry with the vertical axis, thinking rectangularly. So we can get that by switching both r and theta with negative r and negative theta and getting back the same value, essentially getting back something equivalent. And then finally, for symmetry with the pole, we're looking for symmetry with the origin, and that will occur if we can flip the value r. That is, if we can make r negative r and not affect a meaningful change on the behavior of the overall equation. So, for example, thinking of that last one we saw, because sine is odd, if we take that value theta, make it negative, and take the value r, make it negative, we will end up with our values there, the negatives canceling out, and we'll get back to where we were supposed to be. That is, if we have negative r equals 4 sine of negative theta, because that function there, sine, is odd, we can pull out the negative, get negative 4 sine of theta, and then cancel out the negatives to return to 4 sine of theta. Where because we can change both of these and still have essentially the same thing, this has that second kind of symmetry, which makes sense if you think back to what that picture looked like, as it was a circle around the y-axis. But to understand this a bit more, we're going to look at another example for how we can make our graphs a bit more efficiently using those symmetry properties. So here we want to use symmetry to graph r equals 1 plus cosine of theta. Now, if we want to use symmetry to make a graph, before we do much of anything else, what we should check is whether or not it fits any of these three patterns. So for the first case, if I take r equals 1 plus cosine of negative theta, knowing that cosine is an even function, that negative by itself actually doesn't do anything. So that's just 1 plus cosine of theta, which tells me that because switching out the theta with a negative theta still returned essentially the same equation, we have that symmetry. That is, we have symmetry with the polar axis. For the second case, if I exchange out the r with a negative r and the theta with a negative theta, I have that same thing on the right side. I can pull out that negative and not have it mean anything because of the evenness of cosine, but there's nothing I can do with that r. I could divide it over, but that wouldn't return 1 plus cosine theta anymore. So we don't have symmetry with the vertical axis along the angle pi halves. And then finally, for the third case, well, it fails for essentially the same reason. Negative r equals 1 plus cosine of theta is the same as saying r is equal to negative 1 minus cosine of theta, which is a different polar equation than where we started. So we do not have symmetry about the pole. Now, if we want to graph this, we're going to go through carefully this time, but note that because we have symmetry about the polar axis, about the horizontal axis, we really only need to go until we reach that axis again. And at that point, we'll know that we have the symmetry we want to be able to flip things back over. So here, what we're going to do is take our values starting at 0 and going up by pi over 6s again, because we're usually pretty comfortable with pi over 6s, although sometimes we use pi over 4s. But at 0, we have r equals 1 plus cosine of 0, which is 1 or 2. Then at pi over 6, we have r is going to be equal to 1 plus cosine of pi over 6, which is root 3 over 2. Add 1 to root 3 over 2, and you get kind of a messy thing that's about 1.87. So understand that we're starting from out at the angle 0, radius 2, and then coming up and in a little bit. Then at pi over 3, we're going to get 1/2. Add 1, 1 plus 1/2, so we're coming in a little bit more. Then at pi over 2, we will be at 1, so we're going to hit that axis even a little bit lower, and then come back around at root 3 over 2. We're at 1/2, so jutting out just a bit on that outside. And then we keep going around there to 5 pi over 6, get even closer. And then finally at pi, we hit 0. We've reached the axis of our symmetry. So when we want to get the rest of it, we can keep drawing, but really we just need to flip it over along that symmetry and get the shape like so, where this is an example of a particular pattern that is called a limaçon. Limaçon. You get that little accent there on the C that's a bit awkward to pronounce in English. It comes from an old French word meaning snail, where generally we're going to find that if there's ever anything some bit inconvenient when it comes to math, well, you can probably blame it on the French. But anyway, these graphs, limaçons, say limacons if I'm feeling lazy, or even snails if I'm feeling lazier, are of form r equals a plus b sine theta, or minus b sine theta, or a plus b cosine, or a minus b cosine, and generally fall into those sort of heart-shaped patterns. Sometimes the heart-shaped ones are called cardioids, where depending on what the ratio a over b is, we can get inner loops inside of these as well, hence the snail notation, as it were. So this is one example of a kind of shape we can see here. Next, we're going to look at another.